Hello friends, welcome you all to the 30th lecture on functional analysis and its applications. In this lecture, we will discuss the Hilbert space with examples. Content of today's lecture is Hilbert space with examples. Hilbert space. Hilbert space is a special type of Banach space. Definition: an inner product space, order pair X and inner product over the field F is said to be a Hilbert space if order pair X and inner product is complete with respect to the norm given by norm X equal to square root of the inner product of XX, where F is set of real number or set of complex number. That is, a complete inner product space is called a Hilbert space. Or this definition also can be stated as follows. Let H be a Banach space. Then H is called a Hilbert space if it satisfies the following conditions of an inner product. First, inner product of XX is equal to norm of x square greater or equal to 0, and if inner product of XX equal to 0 if and only if x is equal to 0. Second condition, conjugate complex of the inner product of xy equal to inner product of yx, and inner product of alpha x y equal to alpha into inner product of xy. Fourth, inner product of x plus y z equal to inner product of xz plus inner product of yz. For all x, y, z, the element of H and alpha belonging to F. Examples of Hilbert space. First example, consider the Banach space L2n consisting of all n tuples of complex number with the norm of a vector x equal to n tuples x1, x2 and so on xn, defined by norm of x equal to square root of summation I is equal to 1 to n mod xi square, and the inner product of two vectors x and y respectively as n tuples of x1, x2 and so on xn, and y1, y2 and so on yn is defined inner product of xy equal to summation I is equal to 1 to n xi yi bar. Then L2n is a Hilbert space. Okay. Here, if y is equal to x, that is inner product of xx, that is norm of x square, and right side summation I is equal to 1 to n xi into xi bar, that is mod xi square, this one. Therefore, norm x is equal to this. Okay. So already we have proved this inner product satisfies the all conditions of inner product. Okay. And already we have discussed L2n is a Banach space. That is, L2n is complete. Okay. So as per the definition, if H is a Banach space and satisfies the all condition of inner product, that is Hilbert space. So L2n is a Hilbert space. Okay. We have proved in lecture 27 L2n is an inner product space. Also we know that L2n is Banach space, so it is complete, hence it is a Hilbert space. Example second, the inner product space L2 for vector x belonging to L2, that is x has infinite dimensional x1, x2 and so on, and y is equal to infinite dimensional y1, y2 and so on, both belonging to L2. Define the inner product of xy equal to summation I equal to 1 to infinity xi yi bar, equipped with the norm given by norm x equal to square root of the summation I equal to 1 to infinity mod xi square, which is a Hilbert space. Okay. Proof is similar as example first. Okay. So this is example first. Next example, LP space. The linear space LP, P lies between 1 to infinity, P not equal to 2, equipped with the norm given by P's norm x equal to summation I equal to 1 to infinity mod xi power p whole power 1 by p for all x equal to infinite dimensional x1, x2 and so on up to infinity. That is x equal to x1, x2 and so on. Okay. So I is equal to 1 to, here I is equal to 1 to and so on. That is LP is not an inner product space and hence not a Hilbert space. Okay, we can check it by parallelogram law. Okay, if satisfies the condition of parallelogram law, so we can say that the given space is inner product space, otherwise not an inner product space. Okay, so here let x equal to -1, -1, 0, 0 and so on belonging to LP, and y also infinite dimensional -1, 1, 0, 0 belonging to LP. Then x plus y equal to -1, -1 that is -2 and -1 plus 1 that is 0, 0 plus 0 that is 0 and so on, and x minus y into -1 minus -1, okay, that is +1, -1 plus 1 0. Second point, -1 -1 that is -2, 0 minus 0 that is 0, 0 minus 0 that is 0 and so on. So x plus y -2, 0, 0 and so on, and x minus y equal to 0, -2, 0, 0 and so on. Now we have norm xp. Okay, so x norm of x p equal to mod x1 power p plus mod x2 power p plus and so on mod xn power p plus and so on whole power 1 by p. Okay, so here mod -1 power p, that is mod -1 that is 1, 1 mod 1 power p that is 1 power p that is 1. Again mod -1 power p that is 1 power p that is 1 and 0, 0, 0. So 2 whole power 1 by p, that is mod x equal to 2 to the power 1 by p. Similarly, norm y under pth norm it is also 2 to the power 1 by p. And norm x plus y, as per this formula, norm of x plus y under PS norm is 2, because here minus 2 power p plus 0 and so on. Okay. So mod of minus 2 power p, that is 2 power p and whole power 1 by p, that is norm of x plus y is equal to 2. Similarly, norm of x minus y under PS norm is 2. Hence, square of the norm x plus y plus square of the norm x minus y equal to 2 square plus 2 square, that is 4 plus 4, 8. Okay. And 2 into norm x square plus norm y square. So this one 2 to the power 1 by p square, that is 2 to the power 2 by p. And norm y square, this is also 2 to the power 2 by p. Okay. So both same. So norm x square plus norm y square, that is 2 into 2 to the power 2 by p. And already 2. So we have value of this 4 into 2 to the power 2 by p. Okay. So parallelogram law, we know that the parallelogram law, norm of x plus y square plus norm of x minus y square equal to 2 into norm of x square plus norm of y square. Okay. So here left hand side is 8 and right hand side is 4 into 2 to the power 2 by p, which is not equal if p not equal to 2. Okay. Thus LP is not an inner product space and hence not a Hilbert space, although it is a Banach space. But if P is equal to 2, then parallelogram law is satisfied. Okay. Norm P satisfies the parallelogram equality, because here P is equal to 2, that is 2 by 2, 1, that is 2 into 4, 8. So left hand side equal to right hand side. So equality of parallelogram law hold here. Hence L2 is a inner product space and a Hilbert space. Next example. The inner product space CAB equipped with the norm given by infinity norm x equal to supremum of mod xt, where t belonging to closed interval AB. Okay. Here x belonging to CAB. CAB means set of all continuous linear functional in closed interval AB. So CAB is not an inner product space and hence not a Hilbert space. Proof. We prove by example. Let xt is equal to 1 and yt equal to t minus a upon b minus a for all t belonging to closed interval AB. Okay. So x and y belonging to CAB. This implies that xt plus yt is equal to 1 plus t minus a upon b minus a, and xt minus yt is 1 minus t minus a upon b minus a. Now we have norm x is equal to supremum of mod xt. Okay. So this is 1, that is norm x under infinity norm equal to 1. Similarly, norm y is equal to supremum of mod yt, under T belonging to closed interval AB. We have 1 because here T minus A upon B minus A, supremum value at T is equal to B. Okay, so B minus A upon B minus A, that is 1. And also X plus Y is equal to supremum of mod xt plus mod yt. So supremum value of 1 plus t minus a upon b minus a is 2 because maximum value of this at t is equal to b, that is b minus a upon b minus a, that is 1 plus 1, that is 2. Similarly, x minus y equal to 1 minus t minus a upon b minus a. So supremum value of mod xt minus yt is here maximum value of this 1, here minus. So if t is equal to a, we have maximum value. Okay, so a minus a, that is 0. Mod of xt minus yt equal to 1. Okay, here supremum value of mod xt plus yt is 2. That is norm of x plus y is equal to 2 and norm of x minus y is equal to 1. Hence, square of the norm of x plus y plus square of norm of x minus y equal to 2 square plus 1 square, that is 5. And 2 into norm of x square plus norm of y square, that is 2 into 1 square plus 1 square, that is 2 into 2, 4. So parallelogram law, this is not satisfied. So left hand side is 5 and right hand side of parallelogram law is 4. Okay, therefore left hand side not equal to right hand side of parallelogram law. Therefore, infinity norm does not satisfy the parallelogram equality, thus CAB is not an inner product space and hence not a Hilbert space, although it is a Banach space. Next example, the inner product space CAB, the set of all continuous real valued function on closed interval AB. For vectors x, y belonging to CAB, define inner product of x, y equal to integral a to b xt conjugate complex of yt dt. Equipped with norm as norm of x equal to square root of integral a to b mod xt square dt. Okay, here in inner product, if we take y is equal to x, then norm x square is equal to this, that is norm x is equal to square root of this integral. So CAB is not a Hilbert space under this norm or under this inner product. Why? Because CAB is not a complete with respect to the above norm. Already we have proved this is not a Banach space. Okay. So this is not a Banach space, that is not a complete space. Okay. So it is not a Hilbert space because Hilbert space is a complete inner product space. It satisfies the all condition of inner product, but space is not complete. So it is not a complete inner product space and hence it is not a Hilbert space. In this lecture, we have discussed the Hilbert space with examples. These are the references which have been used in this lecture. Function analysis, Dover publications written by George Beckman and Lawrence Naresi. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publisher, written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.